Good afternoon, everyone. For the first session, I would like to request Mr. L.K. Gite to chair the session. And simultaneously, I would like to request Dr. M.M. Shikare to deliver his seminar.
So, as you notice, the and the title of the seminar is computer oriented. The title of the seminar is computer oriented. Whereas the applications are mathematics. So, when you want to study the applications of mathematics in computer science, you should really know which part of mathematics is being which part of the computer. You should know mathematics, you should know computer. You should very clearly identify the structure of the concept in mathematics. You should really identify the part of the computer where this concept is applied. So, one should know both the subjects. So, I have been trying to make the things as clear as possible. So, next. So, here is the outline. I won't take that. Outline of the talk is introduction to the subject, then some basic notions about the computer science and mathematics. Basic notions, basic understanding about computer science as well as mathematics. Use of mathematics in computer science. On the other hand, use of computer science in mathematics. And then at the end of, I would like to do some references to this. So, here we would like to say the importance of mathematics and computer science. That both of them are extensively used in many fields, as I have spoken earlier. Both have influenced the other and led to many advancements. Then the synergy between the two have even led to the increasing computational mathematics, which is one of the important points. A view that may continue to be the intersection between the mathematics and the computer science. And it is understanding that mathematics is supposed to be the fundamental importance in computer science. So, third occasion, real-world problems are often expressed mathematically. One can model a real-world problem in the form of a mathematics model. Some problems may be modeled as a graph structure. Some problems may be modeled as a linear equation. Some may be modeled in the form of the linear equations. So real world problems can be modeled in the form of a mathematical structure. Mathematical theory is used to solve the problem and hence to get the solution to the original problem. And finally, we say that the computational mathematics successfully combines the two mathematics and research. Now, what is the understanding? It is not just the computer lab. It is not the courses that is listed under the computer science course. So what is all about? If someone wants to say a few things about, if someone wants to ask the other person what is computer science, the definition or the information here may not be absolutely 100%, but at least it should be convincing. That it is the study of the theory and experiments and engineering on the design and use of the computers. It is scientific and practical approach to computation and its application, and the systematic study of visibility, structure, expression, mechanization of the methodical procedures that underlies the acquisition, duplication, processing, storage, communication of an execution. Or what can say alternatively that computer science is the study of automatic algorithmic processes that scale. A computer scientist specializes in the field of computation and the design of the computation system. And then research fields such as the computational complexity theory are highly abstract. So, what is the abstract and non-abstract? So, the meaning of the word abstract, we also study abstract algebra. Or here we talk about the complexity theory is abstract. Abstract means the thing that doesn't have the color, that doesn't have the smell, that doesn't have, you cannot see the thing, just only on the arithmetic theory, with the help of the action, we have to do the things. So, some of the things are abstract, while fields such as the computer graphics are vigilant. So, you should know the difference between the abstract things and the visualizing. Visualizing things are more easy to understand. The abstract things, you have to keep in mind several things and understand. On the other hand, what is mathematics? Because if someone asks what is mathematics, some people who study geometry would say that it is the study of lines, planes, other things. If someone who is studying the abstract algebra says that it is abstract things, doesn't have the smell, doesn't have the color, only actions, and if someone studies the differential equation, he just equations that they study. So, the definition of mathematics is not unique. More or less, you can say that it's something like when six blind people were asked to describe how the so you know the story of the blind people. Blind people wanted to describe how the elephant looked like. Those who have touched the tail, they felt that the elephant is like a stick. Those who have got came in contact with the neck, they said that it is like a throat. Those who touch the stomach, they have different kind. So everybody has.
이거 음악은 뭐는 그 마이크 켜고 하는데
Like trial and error method. Like defining trial and error method. You got trial and trial. So, defining mathematics is very great. Right. But we have to do some description and all these subjects will be covered. All these subjects will come under one information. Unify the definition, and here that's what mathematics is the study of topics such as quantity, numbers, structures, space and change. There is a range of new philosophers. That's why I said that you cannot do it uniquely. Ask various people to describe and they will have the different opinions. And then here, what we do in mathematics, we sit out the patterns and use them to formulate the conjectures. What is a conjecture? Conjecture is a mathematics statement. Because in mathematics, you have conjectures, you have theorems, you have propositions, you have lemmas, you have theorems. So what is the difference between all of them are the mathematical statements? Conjectures are those mathematical statements where you verify that the examples they are true. They are not only true. When you provide the proof to the conjecture, it becomes a theorem. What is a lemma? So theorems are major mathematical statements. What is a lemma? Lemma comes before the theorem. Lemma comes after the theorem because lemmas are useful during the theorem. So they come before the theorem. Corollaries come after the theorem. We have seen that corollaries never come before the theorem. Because corollaries are the special cases of the theorem, so they come after the theorem. Propositions are the mathematical statements of the small or basic points. So conjectures will make your mathematical statements. And then try to disprove it. If the conjecture is proved, it becomes theorem. If it is disproved, that will be counterexample given, the conjecture is disproved. Okay? So what we do here, we make the conjecture and try to do the proofs. And then other things are. Thank you, Vikhe. What is the conjecture? It is the science that deals with the multiple shape, multiple arrangements. That is all of this. Are shifted everywhere. The hall in which we are staying, some kind of gravity helping, some kind of symmetry helping. You, the person who has utility, may not realize that he is using that. But he really has used or and the need of the man arose based on the great amounts of the society. The more complex the society, the more complex the society. Primitive type, there are other types, where it's really more than the ability to talk. But also we have a man ability to produce and research and to. So how the number they have developed. And it may be that some of the things that in private life or primitive life, when the people want to count the taxes, they use tables and small scrolls. But for every chapter, they used to have one scroll. This is how they may not be how many scrolls are there. But for every chapter, they used to use one scroll, one table, one count. This is what the beginning or primitive life to count the things. Next. I think this position is clear. Okay. Because it's a trial and error and it's something. So computer science or mathematics is the title of the seminar. And here we see how computer mathematics, which part of mathematics you bring computer part of. I would like to bring to your attention the journal that is devoted to the subject. So look at the following journal. The name of the journal is Mathematics and Computer Science. There is a special journal. The name of the journal is Mathematics and Computer Science. It is ISN number, it print version. It is online, it is print version. The publisher is Springer. Very reputed publisher and is worldwide available. And the purpose of the journal is the journal publishes high quality on the development of the series and the computer and information science, the design, implementation, and analysis of concepts, and the software tools for mathematical application, research, and the integration of computer science or scientific and legal science. And also the journal participants give special issues on their own selected topics. Related to the things of the cross if someone wants to study the latest use of mathematics of time, we can consider teacher. But I want to make your time teacher that there is a special journal on this subject. Published by a very limited purpose. Then some questions we should consider before we go for the application. That how exactly is mathematics related? Second thing, how can mathematics help advance in computer science? By using mathematics, how one can understand that how computer science is progressed, how it is progressing. And then do all the branches of computer science require the same degree of difficulty of mathematics? Some part of the computer will require elementary type of mathematics, like multiplication, combination, division, calculation. Some part of the computer or advancement may require like probability, statistical probability. So, not everything will require the mathematics of same degree. And the last question is, what are the advantages of doing applications of mathematics? We will learn advantages of mathematics. How is it? So that we have to, at least you should be able to list out what are the advantages of doing the applications of mathematics. You can also ask the question, what is the advantages of knowing the applications of computer science? This is in both ways. But one way seems to be very usual. Applications of computer science in mathematics are more. They are more usual. They are more available. The applications from mathematics to computer science, they are not so much. They are not so much. And we can give the examples of the applications of computer in mathematics are more appealing. We can give some examples. Then arithmetic, as I said, that very low level of mathematics is useful in computer science. We know the arithmetic operation, plus, minus, multiplication, and division. They are four basic operations for numbers. You make the addition of the numbers. And then we have some conditional operations, like implies, if this implies, or by condition implies. You can notice that in computer science, all these operations are there. These operations are all two mathematics. But nowadays, these operations, arithmetic operation in mathematics and conditional operators, basically conditional operators are like in law. They are also used in computer science. And then same thing, I think we start studying set theory in 8th class. Probably we start studying at the 11th. Boolean algebra start studying at the 14th. Boolean algebra, you can say that the Boolean algebra we can be associated with the circuits. Circuits are basic blocks in computer science. Every circuit we can associate with Boolean algebra. And other way around. So to consider the feasibility or for the purpose of the applications, we consider the Boolean algebra as a mathematics. And one can, as I said, that the Boolean algebra and circuit theory have the close relations. So to study the optimization or the properties of the circuits in computer science, Boolean algebra is important. So it is why what are the parts? As I said that if you try to describe the topics in the mathematics, you require thousands of pages. But you sort out which of them some selected topics and then also relationship mathematics. Next. Then we come to some specific subjects. How many algebras we have? If we try to list the subjects from the linear algebra, algebra. First comes algebra, then comes abstract algebra, comes linear algebra, commutative algebra, so on. Fully. Okay, algebra, then some branches are these 4 types. There are. So from that we use the linear. Math is algebra is called linear. There are other. Abstract and linear, commutative and linear, each of them have their different properties. So linear algebra is the study of linear equations, then matrix determinants and vector spaces. The results of linear algebra have found applications in computer graphics. But part of the linear algebra, where it is used. In computer, it is with both computer graphics. Data compression, network growth, etc. The way computer goes, any mathematics in 2-dimensional or 3-dimensional world is called vectors. Part of the linear. The language of vectors and vectors is an elegant way to describe the way in which an object may be rotated. Vectors of that property. That object may be rotated, shifted, which translated, or made larger or small or scaled. Then images, JPG or video, MPG, and computational algorithms make use of Fourier transform. The part of the Fourier transform is again linear. In all cases, the computation makes use of the fact that in Fourier spaces, information can be put away without disturbing the main information. And further, a computer chip is nothing but it. But computer chip is important for our computer. It is nothing but a matrix filled with 1 and 0. Therefore, linear algebra is used to solve the 1s and 0 to matrix calculations. Computer graphics, as already pointed out, computer graphics uses linear matrix algebra, change the coordinates, geometry, and dynamic factors. Also, we can scale an object, as already pointed out. We can translate an object from we can rotate an object. By a linear matrix, we can draw the pictures. The idea of linear algebra are used throughout computer graphics. In fact, any area that concerns itself with numerical representations of geometry often is connected together with numbers such as x, y, z, which are positioned to mathematical objects called the vector. Vectors and related mathematical objects called the matrix are used all the time in graphics. And then linear programming. That linear programming uses a system of, what is a linear programming? Study linear programming, linear equations. There are constants, and the purpose is to optimize the function. It can be actualization or it may be application. So, linear programming uses a system of equations called constants to maximize profit function and minimize cost. All such problems often that we are solved by computer using linear algebra. And then linear algebra are activities and raised to direct proportions to the English computer. Which leads to generation of high-level software together. The demand for even correct capabilities. Computer science is simply the beginning to the exposure to parallel processing and large-scale computation. If you go to the art of this computer, parallel processing and large-scale computation, some kind of mathematics, namely linear programming has been. And then we can formulate the 3-dimensional programming in computers. So, 3D program is the most feasible and obvious application where linear algebra is good for all placements, rotation, scale, camera orientation, physics, that is position, collision, and even lots of other problems. Beyond that, again, anything having to do with the physical world will probably use linear algebra. Physics simulations may be stress testing, GPS data, or scale saving. Most of the math can be done by libraries or you. But a good solid knowledge of the concept of the linear algebra will give you greater ability to code efficient and powerful. And then how this linear algebra useful in hardware, software, or different ways. So we said that there are several aspects of computer science: hardware, software, and people. So yes, linear algebra can be used in all the categories. For example, in hardware, how do we use in hardware? To design optimal design for pre-transmission, yes, or pre-follow. Then Kirchhoff's law, EDC. The secretary know that the Kirchhoff's law. So we can use these algebra to design the circuit computers with that the Kirchhoff's law. And the optimal design for the Kirchhoff's law. In software, math operations on array or coordinate coordinate transform, etc. In people way, optimal allocation of resources amongst software development team. Thus, this linear algebra is very useful tool for solving allocations, optimizations, and such for complex systems with multiple layers. This is how the first part of the linear algebra used. So,
So पूर्ण राईट घेईल कन्सेंट्रेट कितना नंबर स्लाइड चालू चौदा का
some idea of linear algebra and its uses in computer science. The key part of the data algebra is techniques. Now, what purpose of computer science? Now, we consider
next yes.
So, another branch of is discrete mathematics in computer science. So, what is the discrete mathematics and how discrete mathematics? I will not walk you through the case of this. But the example of the discrete mathematics will be integers. Example of the not discrete, continuous mathematics is the points of the circle. So, understanding discrete mathematics, continuous mathematics different. So, discrete mathematics uses a range of techniques. Some of these is said on how we can do this topic. So, we mentioned this topic in discrete mathematics. So, self function derivation, group theory derivation, number theory, the math and the arithmetic, then counting and computing, probability for stack detection and complexity. Those who are using this image, you know that there is one folder known as stack. So the probability has something to do with it. Logic is used for group of program practice. Graph theory is used for accessibility and the social network. Higher data and regular languages are used for comparison. So, I think we just one slide here. Now, here, just go to it. The graph theory interpretation. Graph theory, in what way it is useful in computer? So we like to bring to a calculation that the computer network, we can model how the computers are connected to each other in this graph. So graph is basically a structure which involves vertices or nodes and edges joining to. So here, computer network can be considered as a graph model. So the nodes are the individual computers and the edges are the network connections. And the graph can be used, for example, to go places as quickly as possible. So modeling computer network as a graph. Then in vigilant map, nodes are intersections or streets. Intersections in the intersections of the roads, or they can be taken as streets, as vertices of roads. And the edges are roads or highways. And then we may have directed edges to capture one-way streets and weighted edges to capture distances. The graph is then used for determination of direction, for example, in GPS units. So the base of the GPS unit is nothing but the part of the graph. And then next, on the internet, nodes are web pages. And the edges are linked from one web page to another. So here we take the graph related to the web pages. And then this graph can be used to write the importance of each web page for search results. For example, the importance of the web page can be determined by how many other web pages are pointing to it. Divided directly. So between any page there is a direction. And especially how important those web pages are. So we can determine these aspects properties. Then another notion in graph theory is the rooted tree. Don't have familiar with the graph theory. Not a tree is a special type of graph. Tree is a connected graph which has no cycles. That is no. So here the tree is the rooted tree. And why graph tree are called tree? Because they look like trees. Fish is definitely like trees. So they have the property. So similar property is not for this graph, so they are called a tree. Similarly, the rooted tree. The root of the tree has the property that the flow, the water, works from the root to the any branch of the tree. So you see the definition of what is a rooted tree in graph. The directed tree is a diagram whose underlying graph is a tree. You just neglect the arch and look at the underlying graph, it should be connected at first. So this is about the directory. And a rooted tree is a directed tree, having a distinguished vertex called the root of the tree. So that for every other vertex V, there is a directed path from R to V. So there should be a directed path from R to any other vertex of the tree. And right rooted tree, the arrows are usually omitted from the R. See the directions of the R is always away from the root. And here is one example of the rooted tree. R is the root of the tree. And you can say that you take any other vertex, there is a path from R, directed path from this root to any other vertex. So an example of the rooted tree. I have mentioned how rooted trees are useful in the computer application or in computer. So next slide, so rooted tree application, and the application is for data organizing. So rooted trees are used to store information that is organized into categories from sub-categories. And the Dewey Decimal Classification System for libraries is one such example. The system starts with 10 broad subject areas. Each assign a range of numbers. More specialized areas within a given area are assigned to sub-areas. Eventually, single numbers are assigned to the specific subjects within area. And these subjects are further broken down by using this practice. So the rooted thing is the model video. So how books in mathematics are classified in the daily decimal subjects. So we need to understand how what does this figure represent. So this is a rooted tree. Okay, this is the root. These are the other vertices of the rooted tree. And you can read from this root to any other vertex by the tangent line. So rooted tree. So what is being done here? This root, you can say that this consists of all the subsets. Okay? And then these nodes specify that every single numbers are assigned to the specific subject in the area. You can say that all the roots here. Then here specialized subject, and when thinking of the mathematics, suppose 7 is assigned to mathematics, this consists of mathematics subject. And then next you consider financial mathematics. For example, applied mathematics, pure mathematics, some other. In pure mathematics, you think of the analysis, you think of the algebra, you think of the geometry. When it comes to the algebra, you think of the linear algebra, think of the arithmetic algebra. And this is how the classification takes place, or this data is stored. Some small example where we can realize that the concept of the rooted tree, graph tree, has been used for data organization purposes. Next. So what we have said is that some part of the mathematics is how we calculate. Now we go into different direction. How some part of the computer is used in mathematics. And I illustrated with one example. Here is the four collections picture. In map, the map of countries. I write in short part. Any map can be colored with just four colors. You know the map of India. You know the number of regions. And you have seen the available colored maps. And you must have noted that not two neighboring regions are colored by the same region. Exactly, because otherwise there is a border problem. MP and Maharashtra, they have different colors. Karnataka and Maharashtra, they have different, otherwise there is a border. Of course, the figures are very different. So, the problem is that we don't give the attention how many colors are used to color the regions of the map in such a way that the neighboring regions receive the different colors. But the conjecture, as I said, that conjecture is a mathematical statement. When you verify by the examples, you take a map of any number of regions, you try to color it, you can color it with four colors. That is true. You can color the map having the 100 regions. You can color the map of 10,000 regions or 10,000 states. It is possible. So, conjecture. Any map can be colored with just four colors. That's it. Here's the example. Map of this is the map of the USA. Alright. And you see that how many colors have been used. So one is red. So red, then blue, then green, and then village. So just four colors are used. Number of friends you can count together. 30. So just example that the map of USA has been colored with four colors. Now how to prove it? How to prove it? You may have a map, play the map, having 10,000 regions or 10,000 states. And you said that just four colors are to color the map in such a way that neighboring regions should be different colors. So the problem was raised next. Some background of this problem. So this is a long-standing conjecture over the era. Long-standing. Originally proposed in 1800. The problem, the conjecture was stated in 1850, and the first statement said that it has been proved with the help of the computer. Who proved it? Patil and Vikhe. In which year? 1970. And let's get the chromatic number. What is the chromatic number? the number of colors required to color the vertices of the graph in such a way that adjacent vertices is to the different. That is the chromatic number. So the chromatic number of the planar graph is no greater than 4. So I'm very happy. So this relies this idea analysis carried out by the prosecution. And the proof was done with the computer, with the help of the computer. Sometimes the conjecture was false. If the conjecture was false, the counterexample would have been given. There should have been some graph for which 4 colors are found. I have to check this. In one of 1933 divisible, so they have formulated computations, and there were 196 divisible computations. Lateral gauge number was reduced to 1,076 cases were supposed to be handled. Lateral enhancement by Robertson, Kanya, Seymour, and Thomas reduced that number 60. So number of different cases have been introduced, and many vehicles are one region touching all of them. Not understanding that the surrounding regions can be served with only 3 colors. So people earlier did not realize that one region can be colored, that is the regions around one region can be colored just by 3 colors, because it was more. So we have some regions, the neighboring regions should be able to be colored by 3 colors. So this was settled in 1736, and great help was explored from the computer. But the tragedy is that mathematicians did not approach this proof. They said that for mathematics proof, you require one step, from the first step, in the second step, from the second step, in the third step, you require step by step. That is not step by step. Several help, great help was derived from the computer, subjects the calculations, it was taken from the computer. So it is not true. So mathematicians do not approve this proof, so it is remaining again as a conjecture. It has not become the theorem. It is still remaining a conjecture. No proof has been given so far. And then other applications, matrix for writing. Writing the mathematical research papers, mathematical movement, is language of Vikhe. There are some software like text scan, for our software is available for analysis. Mathematical software such as MATLAB, ILab, SAFE, your data great step for understanding the mathematical function. Then we are studying the analytics of the generator of the code. Theoretically, generator generates the code. We are not able to read it and get it full code. But now you can see that we have generator which generates the code. Visualize and that makes the difference. There, and we have some lectures on MATLAB, so you can see the effect of MATLAB in understanding the mathematics. So these objects are there, and here is a list of some references, some books, some sites where if you want to go into it and understand the applications of mathematics, computer science, or computer science mathematics, you can refer to the examples. Thank you very much for giving questions.
Thank you, sir. I think I have heard somewhere that if you say something new, if you say something, you will repeat those things which you know. But if you listen something, then you definitely learn something new. And from your seminar, sir, definitely our ideas are getting quite changed, and we get the clear ideas about mathematics and about science. So thanks a lot for your good seminar. For the next session, okay, I would like to request Dr.Vithalrao sir to chair the session. Before this, I think we have to facilitate Dr. Shikare sir. So I would like to request Vikhe sir to file seated. Dr. Shikare sir. Thank you, sir.